Good afternoon to you all. Before starting, I just would like to thank the invitation, and it's a pleasure to be here. My name is Figueiredo Jardim, Professor of Environmental Chemistry, and I'm in charge of the Environmental Chemistry Laboratory. And what I will present here is the results of our project. We have a thematic project funded by PESP on water quality concerning emerging contaminants in the state of São Paulo. And we also have a PIN CTA. What's this big project funded by CNPq that is also trying to have a first picture of water contamination in Brazil concerning emerging contaminants, with emphasis in endocrine disruptors chemicals. So what I will try to present here is this, what we call integrated approach, what is a new way of looking possible endocrine effects, or trying to quantify estrogens in water and see if the ones we are looking are the ones that are most important concerning estrogenic activity. Before we go on, let me ask you a very simple question. How many years can a human being live? Maximum. No, 120. That's a good guess. Of course, there's no consensus on it, but 120. That's apparently it's a number that came out looking at the physiological structures of our organs and so on, and people realized that. Not me. I'm not involved in this, but people realized that a human being was made to live up to 120 years. Okay, so of course that life expectancy is in Brazil right now is about 70 something. So why don't we live 120 years? Simple. Germs, genes, and the environment. Of course I'm excluding accidents, because accidents is so. But if you look at this, why don't we live that long? Because first, germs. Well, we all know that there are lots of germs that are killing us. HIV, HPV, and many others. Small bugs. Actually, we were afraid of big bugs, and then we realized that small bugs are really lethal to us. And they are here, so germs. The other one that is very important is genes. For instance, this is true. My grandfather died at 56 years old, had a heart attack. My father died at 53 years old, heart attack. I am just overdoing it, because I was supposed following the strategies. I had a heart attack at 43, but I survived. So genes. See, I got it. And there's nothing, so far, there's nothing we can do to avoid this transmission of genes, and of course with them, all the facilities to having either heart attack or cancer. So we know that. And the environment. What we eat, what we drink, and what is in the air that we breathe. So, as an environmental chemist, my major concern is this one. It's trying to understand how the environment saves some years of our life. Or in other words, chronic exposure. What it makes to us and why it could affect me living, for instance, 57, 62, 87, so on. So people try to quantify how much of the environment, what is the percentage of the environment would contribute. to us having a life expectancy much lower than 120 years. And of course, that's a very difficult calculation. Some people say 30%, some people say 70%. Well, I myself don't know. I will not guess and draw a number. But I think that this is quite important. Perhaps as important as germs and genes and these two factors that we know quite well. So, as a chemist, environmental chemist, I'm very concerned about this. And so, when I try to understand or try to quantify how much chemicals, how much emerging contaminants I can find in a glass of water, like this one, for instance, it's about 2,000 compounds. But I really don't know what is the harm it's going to do. And chronic exposure is very frustrating for most of us working with toxicology because we don't know the answers. So if you have a acute exposure, it's very simple to do. Is the person is dead. You look at his dead, yes, he died. But if you have chronic exposure, then it's 6 years, 70 years. And establishing cause-effect relationship is very difficult because there are lots of other factors that we don't understand. So, emerging contaminants are a class of compounds that have drawn our attention recently. Not so recently. There are papers in 1960 calling the attention for possible hormones, synthetic hormones in the drinking water. And we saw a sort of a dormant for decades, and then in the 70s or 80s, we start seeing some papers dealing with the presence of some pharmaceutical compounds in drinking water, in natural waters and drinking waters and so forth. So in the last 15 years, we got a bunch of work devoted or centered in this compounds. There are so many of them that basically we're talking about more than 500 right now. And what are emerging contaminants? What we call them emerging contaminants. People tend to think that if you say emerging contaminants, they are likely to be new molecules or synthetic molecules, but they are not. These emerging contaminants, what they have in common is that, first, they are not legislated. Second, if they are legislated, they were not legislated for the problems they may cause. For instance, take DDT. DDT is also an endocrine disruptor, but the numbers you see in the legislation did not take into consideration this aspect. This aspect takes into consideration, I believe it's teratogeny. But anyway, so if they are legislated, they were not legislated considering problems with the endocrine disruptors or interference in the endocrine system. And of course, there are lots of new molecules that have been produced in large quantities. And also, that's the third aspect, the amount of the chemical that has been produced. For instance, if this new compounds, some of them have a very low production yearly, let's say less than 1,000 tons. So I'm not putting lots of money trying to understand the possible effects. If there are lots of other chemicals that are being produced at much higher levels, much higher concentrations, that the probability of me having contact or being exposed to are much higher. So we tended to focus our attention in production also, and then combine this mode of action and production, so I can somehow select a number of chemicals that are not legislated, but they may deserve our attention. So let's take, for instance, carbon nanotubes. They are important right now. They've been produced in incredible rates. some nanomaterials, especially the ones for cosmetics, for wrinkles, because they act very fast. Take a cream with nanomaterials in the morning, you were 20 years younger. So consumption is being shooting, booming. And many others, like sunblockers, for instance. And also we have to consider that we changed our standard of living, our pattern of consumption in the last 20, 30 years. So nowadays, before leaving home, the average number of compounds that people are using, especially women, are in the order of 10. So think of it. And 15 years ago, there are lots of compounds that we use today that we did not use it. For instance, sunblockers, typical. So this is just an example to show that our pattern of consumption has increased a lot. I used to say that we consume, right now in Brazil, we have areas of highly populated. Like, take the state of São Paulo, 44 million people. We have densely populated areas, and I used to say that we have the consumption pattern very similar to a French. We pay tax as a Swedish, and we have the sanitation of Mozambique. So that's our country. So we have problems of the first word together with problems of the third word. They are together. So this is unique. We have fecal coliform in the water and huge amounts of BPA. Third word, country problem and highly developed society problem. So this demands, of course, some unique or innovative actions to study and control. So let's say a little bit historically what happened. Postwar. Postwar, we've been sort of believing that technology could save us all. That was the mood after the Second World War, and of course that all the problems, the idea is, give me a problem and the technology will solve it. Easy. Well, we'll see that that's not the case. And of course also the lack of information and lack of knowledge, that up to now we know that there are too many questions that we don't know how to answer. These are all real. I mean, I did not make it up. See, these are real. From an American newspaper or one of these American magazines says that they are happy because they eat lard. Lard is banha de porco. Oh, so? Because they believe that that was really healthy. It may be. I did not make it. That's for real. So see, lack of information, lack of time to see how chemicals would behave in the environment. We didn't know it. Actually, up to now, you see every other day they are taking out one of these medicines from being in the shelves of drugstores, because they realize that this compound, instead of healing you, is killing you. So it happens very frequently. So lack of knowledge. I will believe that's only lack of knowledge. But anyway, if you look at the number of chemicals, this figure here, I may say that they vary a lot. Depends where you look. But let's say that we have 11 million substances that are known nowadays. 100,000 are being produced routinely. Every year, we are registering about 1,500 new substances. So every year in the market, we have 1,500 new substances in the working place. And if you look at the regulation in drinking water, of course that we cannot regulate 90,000 compounds. So what we do, we take epidemiological studies take mode of action, and we regulate. Mostly the ones we know are evil, are bad. No, these are bad. So we try to regulate. And in Brazil, we have roughly 40 of them being regulated. So there are many other compounds that are not regulated because, first, because they may be new compounds, and second, because 10 or 20 years ago, we were not exposed to them, but now we are. Take, for instance, synthetic hormones, E2, or ethinyl estradiol. And take the amount now of women that are using this contraceptive method. Highly populated areas. Virtually in Brazil, sewage treatment is roughly 45%. We must take care what the municipality says, because there are lots of words that are being used in Portuguese saying the sewage is being collected or coletado. That doesn't, they really don't say what they do after they collect it. Or afastamento. It's also another words that, look at the IBCCF and you see that. And we really don't know what treatment means. Sometimes filtration, just making this sewage go through this net that is 2 millimeters but wide, just to remove boots and tires and everything. That's treatment. So you must pay attention to this. But anyway, we cannot legislate lots of compounds. So what we have to do is look at nature and see if we see some effects in aquatic, for instance, aquatic communities. If we see some effects, then we must pay attention that something's going on there. And these compounds can go through a water treatment plant and reach you by the drinking water. So look at the environment and try to see any disruption or any changes in communities. If you start seeing that, then we must pay attention and see what's causing that change. And there are very few people that have the sense of looking for years and years and years and see, something's changing. So most of the changes in the environment or changes in policy came from observation, field observation. People go there, they spend hours and hours and hours until they see that something is going wrong. And so after that, you go there and try to understand what caused that change. Well, this emerging contaminants, as I said, they are a vast number of and classes of compounds, like prescribed and non-prescribed pharmaceuticals, plant and animal esterols, natural hormones, synthetic hormones, detergents and byproducts, nanomaterials, flavors and fragrances, industrial wastewater compounds, and so on, illicit drugs and their metabolites, polyaromatic, polycyclic, pesticide, flame retardants. And just to exemplify here how important it is to use this, but we have just finished a study in Brasilia with the federal police, where we calculate that the amount of cocaine being consumed in Brasilia per year is 2 tons. How we did that? Easy. Brasilia, they have 96% of the population is served by the sewage system, and they go to the sewage treatment plant. If you inhale cocaine, 10% of the cocaine inhaled is eliminated as cocaine. Roughly 50% is eliminated as benzoyl-lecognin. So we use this ratio to see how much cocaine has been consumed. And the police said that they estimate roughly 300 kilos of consumption per year, because such estimates are very difficult to be made. First, they cost a hell of a lot of money. Second, information is not very trustful. For instance, you have to go to all those clinics and ask people, how many people are being treated for chemical dependence and so on. But when you look at sewage, they don't lie. It's in there. You go straight. And what is most important is that we can follow tendencies of drug consumption. For instance, you can see ecstasy, amphetamines, and also what is most important, if you smoke crack, comes from the cocaine is under pyrolysis in the crack. So one of the subproducts is not benzoyl cognate. So if you see this ester that is formed in there, so we can follow how the use of crack is increasing. What is a very important information, because crack is a very lethal stuff. I mean, people that they are now selling crack because the most you stay with crack in your pocket before selling it is 6 hours. They need it. Cracker dependence is absurd. So they will do anything to buy this crack. And so we can see that's a real figure. And so in this study, we came out with the figure that 2 tons of cocaine is being consumed per year in Brasilia. And also we can see in which areas there are cocaine is consumed most, and then amphetamines or crack and so on. So you can get very important information out of the sewage as long as you have a good sewage network collection. What doesn't happen, for instance, in Campinas? Campinas treats roughly, the municipality says 57%. Lula has inaugurated 3 times one of the sewage treatment plants there, and it's still not working. But anyway, it's very difficult for us to do the same study in Campinas. So, showing you that sometimes sewage is not just waste. No, hell of a lot of information in the sewage, and we have been using it. And I think that's one type of research that brings a lot of social return. But anyway, talking about emerging contaminants in the 80s, I think that perhaps the first paper that brought some impact was a group of studies in England that realized they found some small amounts of Prozac in the Thames River. I'm not sure if you know Prozac, what it's used for, but Prozac is a very common drug for, I don't know really what it's used for, but anyway, I think depression, yeah. But what happens is it's very interesting, because if you put some Prozac in the water, you see that the fish it takes time. For instance, when the fish detects the prey, some studies reveal that it's getting very lazy to go after the prey when the levels of Prozac goes up. Well, that's what it's made for, isn't it? It works for fish also. So, but anyway, that was the first paper that drew the attention, the international attention. And then in the 90s, so we had this spreading in Europe, and today, basically, I mean, we have this sort of study being widespread in many countries, and of course that there are many others that are not in there. Anyway, what is an integrated approach when we talk about emerging contaminants in water? Being a chemist, I must say that this is the conventional approach. You ask a chemistry, what is the concentration? And we are pretty good in doing this. Well, some of us. So we provide a chemical burden. We say we have that amount of this compound, that amount of this, and then people say, wow, that's good. Or they say, ooh, that's filthy. And after that, that's it. This is the paramount actor to establish ecological health of a given system. After seeing the numbers, we attribute an ecological health to the system. Actually, we may never go there to see how they are. But it's good, it's bad. Okay, give me the numbers and I'll say it's good, it's bad. Well, of course that's not the way it works. I remember in 1987 when I went to do my postdoc on sediment quality criteria. I was working with this person in the United States. He said to me, if you want to know the quality of a sediment, go there and ask the people that live there. If they say it's good, believe them. If they say it's bad, believe them. The problem is that we don't know how to speak their language. So we must learn it in the laboratory. But that's the way you should do. So, what is an integrated approach? For instance, we are looking at strogenic activity. So, we do strogenic activity in the samples. If we got a good a very high levels of response, then we must go and look at which compounds may cause this. So what we are doing here is first doing the response. And when we see the response, the biological response, then we go back and say, well, let me look at this compounds that I know that they have strogenic activity. And then what I do, we are now doing, for instance, routinely 15 compounds. Well, I take the concentration of 15 compounds, taken in a matrix, and look at the biological response, and try to correlate it using a sort of robust statistic or chemometric. And then they may tell me, look, you are looking at this 15 compounds, and none of them can explain the strogenic activity. Try to find another one. Or this one are good, and this one here. Perhaps both of them have a synergy response, and then we may find it. So anyway, that's the approach that we are using. The problem is that some of these assays, the biological assays, they are not well developed. So we are still, when you look at this scenario, we have very good analytical machines, chemical machines, that they are able to say that the concentration is 0.1 nanograms per liter, plus or minus 40%. This is pretty good. But on the other hand, the assays that I'm using, the biological, I hope they don't give false positives, because they are not well developed at this particular stage. We are learning how to do biological assays. So perhaps in a future, in the years to come, in the near future, we may have much more reliable biological assays to tell us, look, this is true, this is believe me, because we still have some in vitro response that are different from the in vivo response, and that causes a sort of a problem to interpret these results. So anyway, I will show here some details of our project in the state of São Paulo. Why we select these points here to study raw water and drinking water? Well, easy, because here is Ribeirão Preto. 100% of the water distributed to the population comes from the underground. A very confined aquifer called the Guarani, well protected. So this water here that people drink is underground. Should be a very good water, because they suck water from 700 meters below ground level. So we believe that this water here should be the one percent lowest or none, or eventually below detection limits of some selected compounds. And of course, if this is the raw water that they are using, after the treatment, it's very unlikely that it's going to be contaminated with hormones, for instance. Second one, São José do Rio Preto. It makes 70% of underground water Now they take water from the Bauru and the Guarani aquifers. One is more vulnerable, the Bauru, but the Guarani aquifer is also well protected. And 70% of the water comes from surface water. And the surface water was quite reasonable quality. Why we know that? Because the state agency, CETESB, it classified the surface water bodies according to drinking water supply. They have an index, it's called IAP. That's the index for water supply. So we took at the CETESB book. Every year they produce this, and we look at how they classify these water bodies here. And here in this area, Campinas and Serquillo, Guarulhos, they all take 100% of the water from surface water. And we select these four places where the water quality range from good down to very bad, according to the state agency. So we have the whole scenario in terms of water quality: drinking water, raw water that is used for water for drinking water. So the idea is let's see what is the quality of the water, the raw water, and then after water treatment plants, how the water that is served to the population is in terms of endocrine disruptor chemicals. Well, the samples that we have been doing many samples here. And besides this project, we also do some raw sewage, for instance, at the hospital to see what's new, what's coming out of this hospital sewage. Lots of cocaine, for instance. But don't you ever think of drinking sewage in terms of cocaine, because it doesn't worsen, okay? So, finished sewage, finished water, bottle, tap, water treatment, and so on. So, we've been doing lots of studies besides the project. But, so, the estrogenic activity. We have the biologic analysis, of course, in vivo and in vitro. And in vivo, normally what they do is, we have one student right now from Botucatu. She's doing a study on ovary. I'm not very familiar with what she's doing, but I know that she's administrating water, concentrate of water, because what we do, we take 4 up to 30 liters of water, and we concentrate, and then she's feeding the rats with this water, and she's gonna look at some ovary malfunction or size. And I'm not quite sure. Fish, vitellogene, because that's a protein that occurs only in male fish, and of course that they've seen that lots of fish that in communities close to a sewage discharge, there are lots of feminilization of fish, or in other words, male fish presenting high levels of vitellogene. And in vitro, what we do is we do this cell proliferation assay, and now using yeast cells that being engineered with a breast. I'm not sure, but I think it's human breast cells, and plus the apparatus of the firefly. So we have the response we look at in the luminometer. I'll show a little bit more the things. And we do this chemical analysis mostly using an LC-MS. Well, I think that perhaps one of the first bioassays using recombinant yeast, it was a method that we have to wait 4 days for the endpoint. And more recently, we have these 2 methods that have been used in our project. One is Leskinen, and the other one is the Sanseverino. And what they do is that basically, again, is a modified organism, it's yeast, being incorporates a human cell, a human gene, And then we look at the luminescence. The last method, you need to use luciferin to obtain the light emission, and of course that luciferin is quite expensive. And more recently, the Sanseverino method, they put the whole apparatus from the bacteria into this yeast, so it produces light. So we don't need to use luciferin anymore. And also, I'll show you that the responses are very similar. Actually, the Sanseverino method is more sensitive than the last method. And we got the assay that's in less than 4 hours. So we can do a whole bunch of samples in a short period of time. Well, the advantage of this yeast bioluminescent bioassay is that they've been used for testing environmental samples for estrogenic activity. They are quick. They are cheap, relatively cheap. I mean, they are cheaper than doing chemical analysis here because you can do a whole bunch of that. You can monitor large amounts of samples, and that's one advantage and one disadvantage, because if you have a small number of samples, you basically is going to spend as much money as doing lots of samples. So try to collaborate, have friends, and do for everyone. And it indicates the presence of unknown estrogenic compounds. So the nice of using this type of bioassay is that we never had a false positive. Or every time we see an estrogenic response, we can detect some chemicals. But up to this very moment, I cannot tell you which one is responsible for the estrogenic activity. We are still working that because our data bank is still small, so we need at least 300 or 400 samples to establish a good statistical analysis and see which one is responsible. Basically, I think you've seen this graph today. It's very simple. It's a dose response curve that we do. We calibrate our model, and everyone calibrates with estradiol, and that's our standard for calibrating the activity. And as you see here, that's log of the concentration. Some compounds, the difference is up to 4 or 5 orders of magnitude concerning estrogenic response. And BPA is here, bisphenol A is here, and as you see, compared to the other hormones, it's much lower activity, estrogenic activity in vitro. Remember, this is in vitro example. And also, one thing that is important is that sometimes the samples we work, mainly raw water, they are so filthy that they show some toxicity. So the response doesn't go that high. And we know that when the graph sort of shortens, we know that it's being toxicity. So something is doing toxic effects to this organism, the test organisms, and we have to perhaps dilute it a little bit more and try to get a response that it can go as high as this one here. So it goes up to the top. So you see, after we calibrate it, it's very much like working with dioxins or PCBs, because we refer to the response as equivalence of estradiol. So that's our pattern. So for instance, if you take this response in here, then it's equivalent to this amount of estradiol. So it's reported in terms of estradiol. Although we don't know what is causing this effect. And I must say that this is still a big challenge for us, is to see if the compounds that we are analyzing chemically are important. So far, it is, because we don't get a false positive. But anyway, so if you look at raw water, and you take this is a strong nonylphenol, nonyloctylphenol, bisphenol A. So these are the concentrations that we found in raw water. And then we transform these concentrations according to the calibration graph in equivalents of estradiol. And then we report how much would be with the test, with the luminometry. So as you see, raw water samples, in 92% of them, we got positive estrogenic activity. Raw water, 92. So far in drinking water, we didn't get any response, luckily. But in raw water, yes, I mean, it's very high. In some of them, the response is also toxicity plus estrogenic activity. Well, and now, so if you have here a glance of what is the range that we find in this drinking water. I have one project that's only looking at Campinas water supply, and the other one is the whole state of São Paulo. So if you look at, these are the number of samples, and these are the occurrence. For instance, caffeine. Caffeine is not a estrogenic compound. So far, hasn't got estrogenic activity. But if you find caffeine in drinking water, then the chances of having other compounds are very high. Caffeine is easily removed in even a lousy water treatment station. Removal rates are roughly above 90%. Even if it's not well operated, as the vast majority that we have in Brazil, they are 90% removed. So if you find caffeine in drinking water, go for other compounds, because they may be, I mean, it's almost certain they will be there. And estrone, bisphenol A, ethinyl estradiol, nonyl phenol, triclosan, lots of triclosan. And now there are some, it's been advocated that triclosan in under sunlight could end up in dioxin. And phenolphthalein. Why phenolphthalein? Simple. We try to use phenolphthalein as a internal standard. And then we realize that we find lots of phenolphthalein in drinking water. Phenolphthalein has been used in lactopurg and so on, but it was forbidden. Actually is a suspect carcinogen. But anyway, we still find it, so we cannot explain why phenolphthalein is present in the water. And so, if you see the range here is 1 order of magnitude. So look at caffeine. It's almost 3 orders of magnitude in drinking water. So it varies a lot. Of course that in dry months, in our winter, and the concentration is almost high, always, because we have water flow in the river decreases a lot, and the consumption of water in the sewage is roughly the same. So what happens is that we don't have dilution. And we start with 8 or 9 compounds, and now we've been increasing, for instance, atrazine has been the last one that we incorporated. But unfortunately, we cannot go back and look at all the samples of 1 year, 1.5 years ago. So some of them you see that are the compounds appear. But if you look at here, for instance, nonyl phenol, it's a detergent, it's only once in 80 samples. But if you, for instance, caffeine is 57 and 58, so go for it. And like bisphenol A, roughly 10%, a little bit over 10%. Triclosan, a lot. Groundwater, the ones that were supposed to be very well protected. Caffeine is there. And bisphenol A, and so on. So, if you see that, despite the number are much smaller here, but even phenolphthalein keep on appearing in this groundwater. Surface. And now, if you look at surface water, because we are taking sites very well contaminated and sites that are not that much contaminated, so you see that, again, take caffeine and it spans from nearly 4 orders of magnitude. So, I mean, the concentration of caffeine it varies a lot in the water. But we found hormones, the natural hormones, synthetic hormones, and bisphenol A. Well, bisphenol A is used in most of these plastic pipes. So it's no way, even if the water is not contaminated, like the groundwater, when they pump it, so you detect the bisphenol A. Even phenolphthalein and so on. Drinking water, Campinas only. So, caffeine in drinking water in Campinas is 100%. So, when we took these results to the water concessionary, it's called Sanasa there, it's an autarky, they said, well, but if you're drinking coffee, there's much more in there. I said, yeah, brilliant. But when I drink coffee, I know I am drinking caffeine. When I drink potable water, I don't expect to have caffeine in it. So, anyway, non-legislated. So we still have this problem. And that's not only in Brazil, it's elsewhere. Elsewhere, it's non-legislated compound. So don't give me a number. If you find it, good. But also bisphenol A and the levels. Now, you may think, okay, what does number mean? Is it much or is it? Give me a clue. Please situate me. So, surface water again. And if you see here, it varies a lot, but roughly we have here. We are talking about this is 1 microgram per liter. That's 0.1 micrograms per liter, and we compare our data with a survey that was made by USGS in the United States. This is the USGS survey 2005, where I think it was the most comprehensive studies on very pristine watersheds and contaminates the watersheds. And if you look at, for instance, here, a great deal of compounds, and we found, for instance, diclofenac was the principle of it's an anti-inflammatory. It's called cataflan, has a lot. And our date here is a little bit lower than the average found in the United States. Triclosan and some hormones and so on. But if you look at the other side of this curve, we are in a much higher frequency of occurrence that they detect in the United States. Well, and here it shows, I selected 2 compounds just for you to have a broader view of what this concentration means. This is raw sewage. There are lots of countries here that I've selected through the literature. Raw sewage. And then the wastewater treatment plant effluent. After passing the wastewater treatment and what's discharged in the river. This is surface water, and this is drinking water. So you see here, we come from sewage in black, coming to potable water in different countries. And you see that if you take the average, for instance, then sewage, for instance, for caffeine would be in around 70 or so in that graph here. And if you take here, it's a little bit more difficult, but let's guess that it's around below 1.5 or so. And these are the average. Here is Brazil. So the amount found in the sewage, in the wastewater treatment effluent, in surface water. So we are 1 stage behind. So our surface water is roughly equal what we find in many other countries after the wastewater treatment plant. But it's not a surprise, because most of our surface waters are indeed wastewater treatment plants. Water reuse that people in Europe love. So we've been doing this decades in Brazil. I live in Campinas, so I drink the sewage from Valinhos, and if you have a good sensitivity, you are able to detect some, like my aunt, because I'm drinking their sewage. Anyway, but that's after some years of probing, and they will be able to do this. Bisphenol A, and if you see again, I mean, the levels that we have here are very high compared to other countries. So now you are situated that what we have here, the concentrations are relatively very high. So the conclusions that so far is that bioassays showed to be more sensitive to surface water samples, indicating higher values of endocrine disruptors chemicals than the ones measured chemically. In other words, the bioassays is more sensitive than the chemical analysis. They give me, when after doing this calibration, they tell me that I have more estrogenic activity than when I compare chemically each of these compounds. But remember that the estrogenic activity is normally made with single compounds, as most of the toxicological studies. And in drinking water, you don't have one single compound, but you have, like I said, 500, perhaps 20 with endocrine activity. So you may explain. Expected estrogenic activity based on chemical analysis tend to underestimate the real potency of estrogenic compounds. Estrogenic compounds present a concentration below the detection limit or non-target can contribute to estrogenic activity. Of course, that my chemical assay is not sensitive. I have a limit of quantification. So anything that is below that, I cannot quantify. So it doesn't go and add to calculate the estrogenic activity and compare to the biological assay. The Sun-Severino method showed to be more sensitive than the Lasky method for all samples, although the development of other bioassays to evaluate estrogenic activity in environmental samples is needed. So that's an open field here because we need more assays to do this. We have very few assays and we need to improve every day. LCMS-MS for target compounds was not able to explain all the bioassays results. In other words, the chemical burden alone cannot explain estrogenic activity. We need more than that. The data bank so far available, it's still not robust enough for us to doing some chemometric analysis, the ones we would like to. In general, in terms of estrogenic activity, both surface and drinking water quality in the state of São Paulo show to be similar to the ones observed elsewhere, despite the low sanitation. So indeed, the estrogenic activity obtained in these waters are similar to other countries. But the good point is that we didn't have any estrogenic activity in drinking water. So that's the good aspect of this. Well, I would like then to finish the organizing committee, the FAPESP Fund and agents for funding this thematic project. INCTAA. To my students, this is the work done by Igor, Cassiana, and Fernanda, and many others, and to you. Thank you so much.
In fact, it's not a question, it's a few nasty remarks. When you ask funding agencies for research about comments on what is normally the performance of research institutes, then they say normally research projects result in creating more problems instead of solving problems. Is it this that just starting to talk about emerging, let's first solve the existing problem. That's one thing. And the other thing is we also have to be a little bit more grateful for our ancestors. I think I'm absolutely sure that DDT, for example, saved many more lives than it ever will be able to take. And so you can also consider this environmental burden as a collateral damage of progress.
Yeah, well, normally when I teach, I say to students, look, DDT has this evil side, but has the good side also. And if you take the number of malaria, people killed from malaria in the old Ceylon, now Sri Lanka, still knew it as Ceylon. And when they start using DDT, the numbers just dropped down. It was nearly zero. And indeed, many lives were saved by the use of DDT. But it's just an example saying that sometimes we need time to discover that a molecule can cause us harm. And it can be nasty later on.
Okay, was I just curious about, have you tried to check raw water and drinking water and removal of caffeine, for instance? Or just thinking, we did work with 8 water treatment plants for metals, and we found out that for some metals, the solvent phase, the water treatment plant process increased the solvent. I was wondering if there could be a circumstance that caffeine could be released by the mud that is deposited in this water treatment plant.
We, in 2 of the cities, we are working in the water treatment plant. That's Igor's thesis. And so he's looking at every operational unit and see how much is the removal, and then coming out at the end of the water treatment plant with the removal. And we know that in caffeine is largely removed during the treatment. The average is 90%. So the chances of being, let's say, a recontaminated in the process are virtually none.
Concerning the bioassay, you comment, you have to be aware that you have a mixture, you know that, and there are many possible interactions between the compounds in the mixture. Additivity is just one possibility. You can have many different possibilities. This is not well studied so far. You see, perhaps you have one compound who is isolated, is highly estrogenic. If you have another one that is antagonist at the receptor, you have no effect, a very low effect in the bioassay. So this is not surprise that you have no correlation. You have not screening for all possible compounds, and also in the mixture you have different interactions. Yeah. But just one thing more about DDT. DDT, remark was very good, and DDT was replaced by organophosphate, and organophosphate sure killed much more people than DDT ever did. And I think it was, I am not in favor to reintroduce DDT for environmental reasons, but the safety record, as far as acute effects are concerned, the organophosphate are much more dangerous.
I'm not sure if you receive a request from the JEF regarding the prioritization of emerging chemicals.
No,
you didn't.
No,
but I was looking and thinking, if you need to prioritize all of these chemicals, what would be your first target?
Production. Oh, actually, I would cross 2 data: chemical production and environmental concentration. Because sometimes we have local or regional problems. And science has a fashion. Like people say endocrine disruptors, and if you are in the United States, they're going to say perchlorate. Perchlorate is the war industry. It's for burning rockets. I mean, so far we did not participate in this, so we don't have perchlorate problems in Brazil. So some of these are local or regional, but what I would be guided by chemical production and environmental concentrations. Cross these 2 and see which ones deserve more attention.